everyone. As Ross introduced me, I am Lionel Fonteneau, a spectral geologist from Corescan. Today, I will be talking about how hyperspectral core imaging can bring new geological insights to the continuous mineralogical characterization of unconventional petroleum systems. Recent work, such as the ones from Ailing, Martini, or Birdwell, demonstrated the effectiveness of HSI technology to characterize unconventional petroleum reservoirs. As we all know, these systems are made of complex textures and fine laminations, which also holds a large variability in mineral assemblages and chemistry. And because this formation exhibits typical fine-scale features, which can be tricky to capture using standard bulks method, sub-millitracal scale HSI has great potential for continuously capture and understand sedimentary processes in unconventional petroleum systems. So now let's go back in time at the beginning of hyperspectral imaging for geological systems. Imaging spectroscopy was first applied to geological materials around 50 years ago using a multispectral satellite which collects up to a dozen of spectral bands. Landsat 1, launched in 1972, was one of the first satellites to collect imagery of the surface of the Earth from space using Rgb camera and multispectral sensor only containing 4 spectral bands. The next Landsat, such as number 4, one containing also band in the sphere, has a clay band, and most of the recent ones have now bands in the thermal infrared region. A decade later, Daedalus 1268 spectrometer was put on an aircraft to collect hyperspectral imagery. Later came other great ones such as Avaris and IMAP. Being closer to the surface of the Earth compared to satellite sensors, it allows a better spatial and spatial resolution and also an increase in the number of bands, hundreds, which is why they are called hyperspectral. But can we get finer scales and apply this technology to drill core, for example? Yes, we can. So back in 2004, they built trials of fitting of a periscope lens to the IMAP instrument, and this then gave birth to the first hyperspectral core imager, or HCI-1 prototype in 2005 by Spectral Systems, delivered to AngloGold Ashanti. And then in 2009, Frank Oni, Neil Goody, and Nindo Tufili created Corescan, which has now released the 4th generation of HCI, which can scan up to 600 meters of core tray a day. So how a hyperspectral core imager collects data? This is the same principle than airborne hyperspectral imaging, but applied to drill core. The current HCR4 spectrometer system using a push broom technology, where a line scan of 50 millimeter wide at 250 by 250 micron pixel is collecting data along the core length. That data is called a hyperspectral cube, which is a combination of a 2D surface scene with a pixel X and Y, with a third spectral dimension represented by 1000 spectral bands. So now let's move to the Corescan HCI technology. The latest model, HCI-4, is a combination of a core photography Rgb sensor at 25 micron, a core profiler at 50 micron, and then 3 spectrometers at 250 micron spatial and 2 nanometer spectral resolution, covering the VNIR and SWIR ranges from 450 to 25,000 nanometers. All these sensors are co-registered, and the system is able to scan at a speed of 25 millimeters per second. And our system is fitting in a standard C container, which can then be sent on-site for being scanning campaign. A wide range of geological materials can be scanned, from whole core to split core to hand sampled and chip scanning blast holes. The VNIR SWIR spectral regions are home to electronic and vibrational absorption features. In the VNIR, the crystal field absorption features, or CFA, is the main electronic process which allows the detection of transition metals such as copper, iron, nickel in oxides, and OH-bearing minerals. Whereas the vibrational absorption features are represented by combination and overtone of the fundamental stretching, and bending observed in the mid-infrared region. These vibrational processes allow then the detection of cationic substitution in the octahedral sheets and also organic matter, to name a few. Because each pixel has a unique spectral image, we can match every single of them against a mineral spectral library and then generate individual mineral maps and also their associated spectral parameters such as composition, relative abundance, crystallinity, etc. Another way of presenting the data is to compile the different minerals into one single mineral class map by assigning a color to each mineral. On the right here is an exhaustive list of minerals active in the mineral sphere, which can commonly be found in petroleum geology, such as carbonates, clays, chlorides, iron oxides, kendites, organic matter, to name a few. But the HSI technology is not just a bunch of pretty pictures. These images are converted into digital numerical logs, which can comprise mineral abundances, proportions, and compositional parameters summarized in depth interval data files, such as CSVs, for use with third-party geological databases, 3D modeling, and statistical software packages. Corescan images and derived numerical logs can be accessed via Corescan, a web portal delivering secure, high-speed access to your image-based geological data. This online visualization tool can also upload for comparison your own ancillary data, such as your field core photo or wireline logs, for example. And finally, it can be integrated live in other databases, such as Acquire and Leapfrog. When you log into www.corescan.com, you will reach the dashboard when you can select your project and your well of interest. Then, to visualize your data, you switch to the grid hole view, and by default, the RGB photo from the core imagery category will pop up, and the core will be displayed as tag by section or tag by tray. Then you can add multiple panels to compare your other images. These panels are entirely interchangeable. You can also add a mobile scale bar. You also have the option to display the data in downhole view. For example, to view your HSI data, you simply change the category. Here, select the mineralogy categories, which by default displays the mineral class. Within this category, you can select the individual mineral images and, for example, overlay them on top of your RGB photo and can play with the transparency. Then you can hit the mineral composition category, which hosts information regarding the mineral composition, relative abundance, or grain size. You also have the ability to present side-to-side the derived mineral logs and compare it spatially with the imagery. You can display them as bar, line, or point, and also you're able to stack them for comparison or for applying simple math operation. As I mentioned before, you can import your ancillary data. In this example, I uploaded the gamma ray log alongside the lithology log for comparison with the HSI data. And there is another great feature under development, which is the ability to modify your lith logs on the fly. If you are not happy with the lithological boundary, you can either shift it or delete it and save it later on. All right, now let's talk about mapping petroleum mineralogy and texture. Advanced spectral parameters can be extracted for specific mineral groups to provide important information on mineral chemistry and depositional condition. Dolomite and calcite can be separated from each other by tracking the wavelength position of the second overtone of the carbonate feature around 2340 nanometers. When iron is being substituted, it can also be mapped thanks to a specific CFA in the VNIR. As you know, it is important to differentiate calcite from dolomite when logging, as dolomitization of pre-existing limestone can enhance permeability and enhance porosity, which can coincide with hydrocarbon migration. And thanks to the fine-scale spatial resolution of the spectrometer, even cyclic minidric bands of limestone and dolostone can be mapped. Another great spectral parameter which can be extracted from carbonate is the grain size variation. So based on the works from Zaini, when the spectrum is pure, it is possible to map the grain size variation of carbonates by looking at the depths of either the 2160 or 2340 nanometer feature related to CO3 bond. On that example from the Bird Bear Formation, you notice that the calcites have a higher relative grain size than the dolomites, and that the spectral distribution of hydrocarbon is associated with a general decrease in carbonate grain size. Commonly, the speciation of organic matter is widely studied in the mid-infrared region, as it is a host of the fundamental stretching and bending vibration modes of both the aliphatic and aromatic feature. But it is also possible to map the presence of hydrocarbon as both the overtone and combination of the bending and stretching modes are located in the square infrared region. And so by tracking the position of the 1750 nanometer feature, you can determine if the organic matter is more aromatic or aliphatic rich, which can be used as a proxy for maturity. Through spectroscopy is also a great tool for candide fixation, which is important to understand the diagenesis of your system. So in details, dikite from kaolinite, from halloysite, and from nacrite can be differentiated from each other, being spectrally unique, by tracking the wavelength position of the doublet at 1400 and 2200 nanometers. The crystallinity of kaolinite can also be determined by using a spectral ratio between 2185 and 2165 nanometers. And finally, halloysite can be differentiated from kaolinite because halloysite contains additional water molecule, resulting in a deeper 1910 nanometer feature. In this well example from the Tyler Formation in North Dakota, we can notice a spectral relationship between dikite, calcite, chert, and organic matter stains. In certain conditions, chert can be mapped as it is exhibiting a specific spectrum with a negative featureless slope across the spectral range. Some minerals found in evaporite potash environment are also active in the Vinyl Swirl region. Here's an example of the Schaffer Dome in the Paradox Basin in Utah. So we were able to map the alternative beds of kaolinite, halite, and silvite. Sulfates such as anhydrite gypsum and the monocalc can also be mapped in the spectral region. Theoretically, anhydrite is free of OH bonds, but in this well from the Three Forks Formation, this anhydrite carry unique water inclusion, which are spectrally distinct from gypsum. Let's move on to Wyoming, USA, and talk about ammoniation in the Green River Formation. So back in 2017, Corescan scanned some wells from the Energy and Mineral Division, and a particularly charismatic amount of pnictonite in the Green River when mapped alongside other autogenic minerals such as dusonite and analcite. So here is an example of spectra of this project where pnictonite and ammonium-rich Elite-1 mica were able to be mapped using diastic features in the swirl related to ammonium. The presence of analcime and dusonite is also quite consequent in this basin, as well as organic matter, which is quite high in aliphatic moieties according to Birdwall. That observation was also confirmed by the spectral data, as the example spectrum of organic matter from this project exhibits strong CH2 and CH3 aliphatic related features. The identification and mapping of minerals within mud rocks using hyperspectral technologies can be quite challenging, but can be overcome using high signal-to-noise instrumentation coupled with high spatial and spectral resolution. Here's an example of chlorite and white mica being identified in a dark mud rock sequence. So now let's move on to a case study of unconventional reservoirs. This case study is part of the well-known Bakken Petroleum system, which is located in North Dakota, USA. That system includes the Bakken Formation, the underlying Three Forks Formation, and lower part of the overlying Lodgepole Formation. In this kind of system, the productivity of a reservoir is in fact directly linked to its variability in terms of mineralogy, thickness, porosity, or permeability, as well as structure and regional to local pressure regimes, which has led to a current increase interest into larger scale and/or continuous core and cuttings analysis, such as CT or hyperspectral scanning. So the data of this case study comes from a 2018 campaign where Corescan acquired HSI data archived in the Wilson Lake Core Library in Penn Forks for a total of 10,000 feet of core from the Milestone Basin in North Dakota. So this is an overview of the different mineral classes which were captured using the Corescan HSI technology. 31 separate mineral classes active in the Vineyard Swirl region were recorded. So these classes were also combined into a single mineral class map for a quick visual overview of trends in the data by assigning for each class a color based on the associated spectrum for each pixel. And the associated minerals are ranked by priority. So let's have a look at the carbonyl composition distribution. So the HSI trends are similar to those logged by Thorley in 2014. The middle Bakken is entirely karstitic but grades to dolomite towards the top, and in contrast is mainly dolomitic in the entire Three Forks, grading into calcites towards the base of U3. Fe carbonates mainly occur in the lower Three Forks and has been described in the literature as light cementation. Data also show a relative increase of dolostone grain size from U6 to U4 and then from U2 to U3. You can note the unusual high wavelength value for dolomite in the lower Three Forks due to mixture with chlorite. So the mica species in this study were readily discriminated using swirl spectroscopy. The recognition of chloride was of particular interest in this system. As its source and distribution in the Bakken was probably poorly understood, here the data show that chloride mainly occur in the middle Bakken and lower Three Forks, and sporadically in the upper Three Forks, and never in the Bakken. Minor compositional variations are noted in chloride species, so the middle Three Forks is mainly iron-rich chloride, whereas the lower Three Forks is more iron-magnesium-rich. And you can notice the inverse correlation between chloride and hematite distribution. Whereas white mica is most abundant in the middle Bakken. Compositions range from muscovitic in notchfall and Three Fork when mixed with montmorillonite to muscovitic fingitic in the middle Bakken and to fingitic in the lower Three Forks over here. The ISM or elite spectral maturity is a great tool for discrimination, to discriminate muscovite from elite from montmorillonite by dividing the depth of a 2200 nanometer feature by the depth of the 1900 nanometer feature. And so data indicates that middle Bakken and upper middle Three Forks are more elitic, and montmorillonite appears in Unit 4 of middle Three Forks and Units 1 and 2 of the lower Three Forks. Other key minerals such as anhydrite, carnallite, and iron oxides were mapped using the Vineyard Swirl in this project. So anhydrites were almost constrained to Unit 2 of lower Three Forks, carnallites in the Bird Bear Formation, and iron oxide precipitation constrained to the middle Three Forks down to lower Three Forks. And by tracking the wavelengths of the 900 nanometer feature in iron oxide, you can estimate the proportion of goethite over hematite. So hematite indicates oxidizing condition, whereas goethite in middle Three Forks, U4, relate to the presence of ferrous iron associated to chloride. Thanks to core-shade interface, it is very easy to compare your HSI mineralogy logs with your lithology logs or wireline logs. One of the spectral parameters which is powerful to get a quick feel of your lithology is the average albedo product. It calculates the average reflectance across the whole spectral region. In this study, this product appears to be a good proxy for grain size variation. For example, the lowest average values were related to the lower Barker and upper Barker shales, which were also correlated with the highest gamma ray log. Another way to get a quick feel of your lithology is to create a Rgb Ternary image combining different spectral features. In this example, the 2340 nanometer depths tracking the presence of carbonate or chlorides were assigned to the green band, whereas the reflectance ratio between 1280 and 1020 were assigned to the red band related to the Fe-rich lithologies or organic matter, and the 2200 nanometers depths were assigned to the blue band, which represents aluminum-rich clays and phyllosilicates. In this third example, lithological units present in this case study were derived using mineral occurrences, spectral compositional data, and albedo to create a custom lithology class map. You know that in additional inputs, such as complementary datasets and/or expert input from project geologists, can be integrated into this type of approach for robust interpretation. The next step with this HSI data will be to combine the large amounts of high resolution and consistent data, here the general albedo and class map, with image analysis machine learning algorithms, such as the one described in Van Rutenbeek works. It is possible to extract and continuously quantify the different chloride texture observed in the three-fork formation, which may link to frackability, according to Bellian back in 2016. And so these discernible patterns in this new work will form the basis for further textual analysis. So to resume, HSI characterization in this work demonstrated the ability to identify and consistently log mineralogy across the BPS system. Previously known mineral and lithological characteristics of the BPS formation were well identified using hyperspectral analysis. HSI also provides continuous high-resolution mineralogy to refine the reservoir characterization. And so several mineral groups and mineral composition were refined or tracked for the first time. For example, carbonate composition and spectral distribution, chloride texture and composition, montmorillonites, anhydrite canalites, oxidation states, and organic matter speciation. And so one of the outcomes is that there is implication for porosity permeability determination at both large and small scales. It can provide basic data that will feed into future diagenetic studies and process models, and may hold important information regarding frackability and well compression design. And finally, it will help to inform studies of other conventional reservoirs in both exploration and production, domestically and globally. I just wanted to share some news with you. So in 2019, Corescan and nuclear researchers Sandra Rodriguez and Joan Esteli did a research collaboration on applying reflectance spectroscopy to coal. And so we found that in the mid-infrared region, using handheld MIR Agilent spectrometer, using the areas of the fundamental switches of the aromatic and aliphatic bond, the more aromatic, the higher the rank. And we also found, using SWIR data from the Corescan HCI system, that we could also predict the hydrogen content by extracting the area of the 2350 nanometer feature related to combination and stretching of aliphatic features. And in late 2021, Corescan will commercialize the new high-level 4, which will be able to acquire data in the mid-infrared region, which will be then able to perform organic matter speciation for petroleum deposits. And finally, on the last note, I just quickly wanted to introduce a scanning campaign that we performed in 2018 with the Howard Ham School of Geology and Geological Engineering at the University of North Dakota, where we studied 10,000 feet of oil and gas cores. So the stage 1 of this project, only the core imagery, is available through this link here. and stage 2 will be accessible around September 2021. And finally, I wanted to give a special thanks to Sam Scher, Brigitte Martini, Stephen Nording, Kate Whedon, and Justin Bauer. Thank you.